Hi, I'm Dr. J, and this is a video about p-values. This video exists in the context of an overall playlist talking about statistical inference from both a Bayesian and non-Bayesian perspective. There should be a link up here to that playlist. There's also a link down below in the description to a PDF version of these slides. Now, I'm going to introduce p-values outside of the context of hypothesis test, which might surprise some of you who are familiar with p-values always being associated with the hypothesis test. But I think there's value in p-values outside of any test at all. Secondly, I'm going to go through two different models as we talk about p-values. I'll talk about the binomial model and normal model. A p-value is the probability of observing a statistic as or more extreme than observed if the model is true. Now there's a lot in that statement right there, despite the statement being fairly succinct. And I'm going to expand it a little bit just to make sure that some of the ideas are clear, and then we'll talk a little bit more about some of the other ideas. So the expanded version that I'm going to have here is the probability of observing a statistic as or more extreme than the one you observed, if the model is true, when you think about the data as being random. So again, this goes back to thinking about the sampling distribution of statistics. Because when the data are random, then the statistics have a sampling distribution. So we're talking about that distribution according to whatever model we're interested in. And now we're thinking about some statistic that we've calculated for the data that we've collected. And we think the data perhaps come from that model. And now the last piece is that we have to talk about what it means to be as or more extreme. That's probably the hardest concept when it comes to p-values. All right, so let's just talk through an example, and that might clear up what we mean when we talk about p-values as a whole and the as or more extreme regions in particular. So the first model we'll look at is suppose that we have, we're willing to assume a binomial model with 13 attempts and a probability of success 0.5. So that's the model that we think accurately represents these data. And then we happen to collect an observation, and we find that we have 3 successes. So y here is 3. All right, this H0, by the way, that notation comes from a previous slide all about hypotheses, and hypotheses being models. And so here, if you want to go back and watch that video, you might want to check it out up here. All right, so we have this binomial model, and we've collected 3 successes out of 13 attempts. So we have a choice at this point, right? The p-value definition doesn't provide us with an explicit, here's the statistic you have to use. And so the first statistic that comes to mind is just the number of successes. So our statistic is 3, though that number of successes has a distribution when this model is true, and that distribution is exactly what we said it was up here. Probably way up there, right? It's a binomial with 13 attempts and probability of success 0.5. when that model is true. All right, so then let's talk about the as or more extreme regions, because that's where it sort of gets a bit confusing. But generally there are 3 different as or more extreme regions. The first 2 are pretty straightforward. The first one is that you can be less than the statistic. So we'll talk about our statistic, the number of successes. What's the probability that it, if this model was true, was going to be less than or equal to 3? Remember, the phrase was as or more extreme. Right? So that as or more indicates that you have to use the inequality with the equal sign. Okay, so here's one possibility for a more extreme region being smaller than 3. Here's another possibility for an extreme region being greater than or equal to 3. And then finally, we have one that's a bit more confusing perhaps, but this one is basically the idea is that before we collected the data, we knew what we expected with a binomial distribution with 13 attempts and probability of success 0.5. The expected number of successes was 6.5, which is 13 times 0.5. And so we can think about the observation that we actually then collect being farther away from that expected value. So this is the notation that represents that idea, being farther away on either end from that expected value. Okay. Here, the 13 times 0.5, that was just the expected value of that binomial random variable. So let's look at these regions as pictures, because that might really help understand what's going on. So here, in each of the 3 facets, is the probability mass function for a binomial random variable with 13 attempts and a probability of success 0.5. Then colored in magenta on each of the facets is the extreme region associated with the 3 extreme regions that we showed on the previous slide. On the very first, the far left facet, we have the less than or equal to. On the far right facet, we have the greater than or equal to. And then in the middle facet, we have this region that's associated with being farther away from the expected value, as or farther away than what we observed. Right? So you can see we have the area there that's 3 and less, but we also have this area up here that is 11, 12, 13, and it must be 14. Okay? One thing to note is that in this setup, that those two areas, or maybe I should say it this way, that in that as or more extreme region on the two directions, on both directions, we have those two areas on the right and on the left are equal. And so we're going to use that in a second when we go to do the calculations. Now let's go and calculate those p-values, the actual values, the probability that random statistic is more extreme, as or more extreme, than our observed statistic if that model is true. So here's our first probability calculation, the probability that capital Y, the random statistic, is less than or equal to Y, the one that we have observed. That's just evaluating the cumulative distribution function for a binomial random variable. So we can do that straightforward, and it's about 0.05. Now we can go the other direction and say what's the probability that the random statistic is greater than or equal to the statistic we observed. We have to do a little bit of probability calculations here, so we have to be, say that probability is equal to 1 minus the probability that capital Y is less than little y. But now that's not quite the CDF calculation because binomials are discrete random variables. And so we have to here do a little bit of mixing up to shift that CDF where we take the y and we subtract 1 to say, all right, the probability that capital Y is less than or equal to the observed value minus 1. If we do that calculation in R, we find that the probability here is about 0.99. The last one, the two-sided hypothesis, we're going to use that idea that we can calculate the two sides, right? Or we can just calculate one of the sides and multiply by 2 because the areas were actually equal. And so that's the statement right here. We're just going to take and calculate that left side, which we already did as the first calculation, and multiply it by 2. And we find that the probability here, or the p-value, is about 0.1. All right, so that was a binomial example. Let's shift over to a normal example just to give you another example to work with. So here is our proposed model. The data are independent, normally distributed with a mean of 3 and a variance of 16. And we have 6 observations. In those 6 observations, we find the summary statistics. The sample average is 6.3, and the sample standard deviation is 4.1. All right, using those two and the sample size, we can calculate the t-statistic. Here is the t-statistic. I'll go ahead and in the updated version of the slides actually plug in the values in addition to the notation, but we find that the t-statistic here is 1.97. Okay, now we're going to calculate a p-value, so we have to choose a statistic. We're going to choose this t-statistic, right? The value is 1.97, and that statistic, we know, if the model is true, has a, what is it? It's a t-distribution with how many degrees of freedom? It's the sample size minus 1, so in this case, 5. And now we can think about the as or more extreme regions. So one is being left of that t-statistic, one is being right of that t-statistic, and the third one is being farther away from the location parameter or the expectation of a standard t-distribution, which has a location parameter of 0. And so it simplifies the notation a little bit here, and we just say here is the probability that a random t with 5 degrees of freedom is farther away than 1.97. Okay, so here's a visualization of those different regions. First off, in all of the facets, we have the probability density function for a standard t-distribution with n minus 1 or 5 degrees of freedom. Colored in aquamarine is the different areas or those rejection regions. So on the far left, we have the less than or equal to. On the far right, we have the greater than or equal to. And in the middle, we have this one that's more extreme, that is farther away from the expectation or the location parameter. And just like before, we can see that the two areas in that calculation are equal to each other. And they're actually, one of them is equal to the right picture. And so we're going to use that idea when we go to calculate the p-values again. Alright, so here's what we're going to do. We're going to calculate the probability that the random t is less than or equal to than our observed t. And we find that the value is, let me look, about 0.95. Now we can calculate the other direction. We can calculate the probability that t is greater than or equal to t. Doing a little probability manipulation, we find that that's equal to 1 minus the probability that t is less than t. But because a t random variable is continuous, that's equal to the probability, or 1 minus the probability that capital T is less than or equal to little t. And now we can use the cumulative distribution function. We can calculate 1 minus that probability, which we find to be about 0.05. Now to calculate our two-sided p-value, we can use that same idea we had in the previous slide, where we have the two areas being equal. And so this probability is just equal to twice the probability that t is greater than the observed t. And we find that it's about, 0.11. Okay, so now the question is, what can we do with these p-values? Right? And so what I want to get across here is that small p-values provide evidence that the data are incompatible with the specified model. Right? So if you see p-values that are small enough, that tells you that something might be wrong about this model. But it's really actually unclear what it is that's wrong. And so if you think about a normal model, right, we write it down very succinctly. We're using this formula, but that formula actually has a lot of context to it, or a lot of parts to it that are all represented in a fairly succinct fashion. Right? So in particular, when we make this assumption for the model, what we're saying is that 1, the data are independent. Okay? The data are normally distributed. They have a common mean and they have a common variance. And so we're saying all of that with this notation. And getting a small p-value is not necessarily informative about which aspects of this model are bad. Right? It could be that the data are not independent. And it could be that the data are not normally distributed. It could be that they don't have the same mean. It could be that they don't have the same variance. And so any of those are really possibilities. And so really, a small p-value just indicates that the data are incompatible with the model and further investigation is required. Alright, so for a brief summary, the p-value is the probability of observing a statistic as or more extreme than observed if the model is true. And small p-values provide evidence that the data are incompatible with the model. We're going to be moving forward and talking about hypothesis testing and how p-values are often incorporated into these hypothesis tests. Hope to catch you there.